Hello everyone. In this video, I'm going to attempt to cover 6.1, 6.2, 6.3, and 6.4. Factoring is essentially what we're getting into here. We're going to see kind of different versions of factoring. It's all factoring. Factoring is one of the more important topics that you're going to learn in this class. It's also one of the more challenging topics to tackle. So I encourage you to come to office hours, to go to tutoring, to really dig in, especially to this factoring material. You're going to do a lot of factoring here, but also going forward if you go on to take other math. So we're going to kind of inch our way into factoring polynomials. So algebraic factoring. First, we're going to just start factoring some numbers and kind of get used to what the concept of factoring is in general before we get into variables. Okay. So find the greatest common factor. First, let me just read this definition. It says to factor a polynomial, and these are not officially polynomials. It says to factor a polynomial means to write the polynomial as a product of two or more polynomials. The greatest common factor of a list of polynomials is the largest expression that divides evenly into all the polynomials. So we're talking polynomials here a lot. That's algebraic. That involves a variable. So before we get there, I just wanted to introduce the idea of greatest common factor. Sometimes you see GCF instead of it being completely written out as greatest common factor. So if we're to look for the greatest common factor of these three numbers, what it means to be a common factor, just the CF part, would mean that this number, this common factor, evenly divides into all of these numbers. Okay? So I know, just based on the fact that all these numbers are even, that 2 would divide evenly into all these, right? We'd have 32, right? 64 divided by 2, 32. 70 divided by 2, 35. 100 divided by 2 would be 50. So 2 would be a common factor of all these numbers. The G, though, means that we're actually looking for the greatest common factor. So although 2 is a common factor, I'm not totally sure that it's the largest or the greatest of all the common factors that we can find for these numbers. So to help look for a potentially larger or greater common factor, we sometimes use what's called a prime factorization. And I'll show you by example what this means. So I'm going to write 64 over here, and then I'm going to actually use what's called a factor tree. I'm going to branch off of that number. And you just need to identify factors. And we already had, well, let me just start with 8 times 8. It actually doesn't matter where you start. I could have started with 2 times 32. But I'll just start with 8 times 8. I know that's 64. And then what you want to do is keep going, keep factoring these ends of the branches until you have nothing but primes. So 2, 2, those are prime, but 4 can still factor into primes. So all of these numbers here, the ends of the branches are all prime. That tells me that I'm done with this factor tree. And that 64 can be written as 2 times 2 times 2, right? These three, times 2 times 2 times 2. Another name for that would be 2 to the 6th. I'm going to do a similar thing for the other numbers. So here's 70, factor 70, 35 and 2, right? Like I was mentioning before. 2 is already prime, then 7 and 5. right, for 35. 7, 5, and 2, these are all prime now. And this would equal 2 times 5 times 7. So this is 70's prime factorization. You can kind of think of the prime factorization like a thumbprint. It's a unique marker for a specific number. No other number has this prime factorization besides 70. Let's do 100 over here. So 100, we have options, right? I can go 25 maybe times 4. It actually doesn't matter where you start. So just pick a place. It doesn't matter. 25 is 5 times 5. 4 is 2 times 2. And all these numbers are now prime. And that tells me I'm done with this factor tree. And we'll see how this plays into finding the GCF. Another name for this would be 2 squared times 5 squared. So now I'm looking at these things. Let me maybe circle in blue. So I'm looking here, I'm looking here, and I'm looking here. The thing is about the prime factorization is that we've broken these numbers down into their essential parts. So we can now see which parts are in common. So for the GCF, I'll kind of just, I don't know, I'll write it up here. So I look at what we have available. There are nothing but 2's as factors of 64. Okay, that's interesting. We have a 2 times 5 times 7. We have a 2 squared times 5 squared. So is there any number that's common? It looks like a 2 is common to everybody, but the most I can take is 1 copy because this one only has a 2. This doesn't have a 2 squared. So it wouldn't have a 2 squared common to this number. So the most amount of 2's that I can take is actually just this 1, 2. So I'll write that down. And that's because we have a 2 here, we have a 2 here, and we have a 2 here, so it's common. Now I move to the next prime. Here's a 5, here's a 5, so 5 is a common factor of these two numbers, right? 70 and 100, that makes sense, both divisible by 5. 64 doesn't have a 5 because it's not divisible by 5. So 5 is not going to come into the greatest common factor because it's not common, right? We would need a 5 in here, and this would be just a different number at that point. So nothing else actually is in common, and the GCF of this would be 2. What about the GCF of something more algebraic? I'll talk about actually this one. So the x's are essentially treated like primes already. So I'm kind of thinking of like, all right, what's the GCF of 12? 6 and 2, 3 and 2. So all these numbers. So 12x cubed would be equal to 2 times 2 times 3 times x cubed. (24x squared). So I'm just factoring the 24. 12 and 2, 4 and 3, 2 and 2. So these are prime. So in other words, another name for this would be 2 times 2 times 2 times 3 x squared. I'll do the other one actually over here. I kind of ran out of room. So 30x, factor 30, we have 5 and a 6, and then a 2 and a 3. So this would be the same as 2 times 3 times 5x. So now I'm looking at these objects here. This one, and this one. As you get better, just to be clear, you're not going to be using this prime factorization. you're going to have quicker ways of doing all this. This prime factorization is just a way of kind of introducing the idea and accomplishing the goal early on. As you get better, we're not going to be breaking things down into their primes. So the GCF. So I'm looking here, I have a 2, and I have a 2 here, and I have a 2 here. I only have 1 2 here. So the most I can take, the most that is common, is just 1 2. Then move to the next prime. The next prime is a 3. I have a 3 here, a 3 here, and a 3 here. So since it's common, I'm going to bring that 3 into our GCF. Move to the next prime. I have a 5. I do not have a 5. I do not have a 5. 5 is only in this first one, or this last one rather. And so it's not common. So it's not going to come into the GCF. Next, we go to the x's. We have 1x, we have 3 x's, we have 2 x's. So the most I can take is 1x, and I'll just write this as 6x. This would be the GCF. All right. So factor polynomials. So you're gonna be expected really to do this more quickly than I have been doing it, and that'll come with practice. What we're going to do, just to tether this to what we just did, is we're going to factor out the GCF of these terms. Notice how they're not just separated by commas. This is an actual polynomial now, right? And it's essentially like we're doing this problem, just to tether it to the previous one, except now we have a polynomial. These things are being added together. Okay, so just looking at the numbers, the coefficient is 8, the coefficient is 24, 8 is divisible by 8, and 24 is divisible by 8. So when I'm factoring this thing out here is where I'm going to write the GCF. I'm going to basically factor out whatever's common. So I know that there's an 8 in the GCF because we have an 8 and a 24. 24 is divisible by 8. I then have a p to the 4th and a p cubed. So the most I can take is a p cubed. So this is the GCF. It doesn't really matter that I label it, but we're just factoring this polynomial. The thing is, now we have to think about, okay, after I factor this thing out, what is then left behind? Right? I have a plus sign that was left behind for sure. But now I'm thinking, okay, if I were to distribute this back in, what needs to go right here and what needs to go right here so that if I were to distribute this back in, I have this object, right? So when you're factoring, you're really not changing anything, you're just re-representing it. So I have an 8p to the 4th. I already factored out the GCF, which is 8p cubed. So I need just a p, right? That way 8p cubed times p makes my 8p to the 4th. Then I need a 24p cubed. I already have an 8p cubed, so I don't need any more p's. So I'll just put a 3 there, right? That way 8p cubed times 3 turns into 24p cubed. So I'll just write this separately, but this is our answer. That's the factored version. If you want to check it, then distribute this thing back in, right? If you distribute that back in, you'll have 8p to the 4th plus 24p cubed, and that's what we started with. All right, I'll do part 2 as well. It's going to be a long video, I think. Here, similar stuff, but just another minor detail. This has a leading negative. In general, what I recommend is to factor out those leading negatives. So I'm not only going to factor out the negative, but I am going to factor out a negative. What gets left behind, we'll need to figure that out. So for sure a negative is coming out. Okay, that's just a general good thing to do. We have a -5 and a +10. So a 5 is shared. So I'll factor out a -5. And then looking at the y's, or the variables, we have 1y here, we have 3 here. So the most I can take, the most that is common, is just 1y. And now I'm thinking, okay, what goes inside of here such that if I were to distribute this GCF, we obtain what we started with. So now I'm kind of thinking, okay, let's fill up this set of parentheses with the appropriate thing such that if I do multiply this in, I get this. So to make a -5y cubed out of a -5y, the only thing I would need would be a y squared. And that, you know, if you just kind of, again, just hypothetically imagine, distributing that back in, then we make our first term here, right? That would accomplish that first term. Then I need to figure out how to accomplish the second term. I have a -5y factored out. I want to make a +10y. So I actually need a negative in here. That way a negative times a negative will be this positive. And specifically, I'll need a -2. All right, that way if you consider, okay, hypothetically distributing over here, negative times a negative is a positive, 5 times 2 is 10, and then we just have our y. So this would be our factorization of what we started with. Okay. Third one here. This is still just 6.1, I believe. So here's an interesting one. We have two terms, and still we want to factor out what's in common. This one might kind of throw you off a little bit because you already have parentheses here. Okay, but this x minus 3 is just one object, and it's attached through multiply. So when I factor out, I'm actually going to factor out an x minus 3 because it's common to both. And then we're going to leave behind something. I'm factoring out this thing as if it's one object because it is. And then I need to figure out, okay, what goes in here? Looks like we'll still have plus. What goes in here to make it what we originally had, right? That's what we're always hoping to not deviate from what we originally had. We just want to re-represent it in factored form. So I don't have a 4x, so I need a 4x here. And I don't have a 5, so I need a 5 there. Again, if you imagine distributing this whole object, right? Just like I was imagining distributing this whole object, or I was imagining distributing this whole object. This is just one whole object, and if I were to distribute it, that would be a way of kind of checking, okay, yeah, we do get back what we had. So I'll write x minus 3, 4x plus 5. All right, on to 6.2. Page 62. So a quadratic trinomial is a type of polynomial. So this is a mistake, by the way. You could just scratch that out. Copy and paste error. So a quadratic trinomial is a specific type of polynomial. So polynomial, basically, that word poly means many. That's an O. Poly, it's about equal to many. When you think poly, think many. And then nomial basically is number. So polynomial just means many numbers. So this is a polynomial. Specifically though, this is a quadratic because of the degree being 2. This is a quadratic trinomial because we have 1, 2, 3 terms. So that language, trinomial, that prefix, right, like tricycle, means that we have 3 nomials, trinomial, right? In other words, 3 numbers. We've also seen binomials actually. I didn't use that language, but this is a binomial, right? 2 numbers, that prefix bi. This right here is a monomial, right? 1 number. So we're going to work on trinomials. This is going to be largely what we are concerned with. So we're trying to factor this thing, this whole thing. Okay. What I'm going to do is explain this in a fairly general way. Okay. So I'll probably just do the first one and the fourth one so that I can fill up this space with this routine. So so this is factoring things such as, let's just write ax squared plus bx plus c. So this is a general trinomial where a is not 0, but it's any other number, b is any number, and c is any number. So for factoring things such as this, so step 1, factor out the GCF. Sometimes this doesn't entail anything, and you actually won't have a GCF. So looking at this first one, what I'm doing is I'm looking at every term and thinking, okay, is there anything common to every term? So these 2 terms share an x, but this term does not have an x. So I cannot factor out an x because x is not common. These 2 terms are divisible by 2. They're also divisible by 4. But this term is not, right? This does not have a 4 or a 2 as a coefficient. So I cannot factor out that 4. So actually in this case, part 1 or step 1 here is actually already done. There's nothing there to do in this case. So on to the meat of the method here. So what you're going to do is calculate a times c. And what I mean is a times c. So for us, we have a 1 sitting there for a. So a times c in this case is 1 times 12. That is 12. Okay, so that's step 2. Step 3 is factor a times c, looking for factors that add to b. And by b, I mean this number. Okay? So I'm going to factor 12 now. So now I'm getting into step 3 here. So I'm going to use a factor tree and just start factoring it. Don't factor all the way down to the primes, but what you're doing is you're looking for factors that add up to this number. Okay? So you might try like, okay, let's try 4 times 3. That indeed does give us a 12. But 4 plus 3 does not equal 8. Right? So if you add these, this equals 7, and that's not 8. So that means we need a different pair of factors. So I'll try that again. Oops, let me not move my page everywhere. So 12, factor it, look for other factors of 12, specifically factors that add up to 8. Yes, 6 and 2. Okay. After you find those factors, So these work, by the way, because 6 times 2 is 12. That's one of the criteria. But also 6 plus 2 is 8. And that's this number in the middle. So that's what I mean by this step 3 is factor A times C, looking for factors that add up to B. Step 4, rewrite bx using the factors we found. Here's what I mean by that. So I'm going to rewrite this original trinomial using the 6 and 2 as coefficients on x that would add up to 8x. Let me just go ahead and write it down. So x squared, I'm not messing with that. But here I'm going to write 6x plus 2x plus 12. So notice 6x plus 2x, I'm using those because of the 6 and the 2. And notice that that adds up to 8x. 6x plus 2x adds up to 8x. All right? Kind of looking around for more paper because I am running out of space. Let's see if I have any. Hang tight. That's okay, I'll just use the space below. So after that, what I now do is factor by grouping. And this is the last step. So what do I mean by grouping? So this is a group. Here's 2 terms right there. Here's another 2 terms. So I'm going to factor out just out of these 2, whatever's in common, and then just out of these 2, whatever's in common. So out of these first 2, they share an x. So I'm going to continue my work down here. What is left behind? Well, to make an x squared plus 6x, well, x is already out front. I need another x inside to make an x squared. And then to make a 6x, I need a plus 6. Right, so if you imagine bringing back in that x, you would create these first 2 terms. Then move to the second grouping and factor out whatever's common there. So a 2x, a 12, the most we can do is a 2. And then what is left behind? An x plus 6. And that is no coincidence. So notice that x plus 6 and x plus 6 both appear. So you need to go to the next step and factor out that commonality. So similar to that previous one, right, where we had this commonality and I just factored it out. So now I'll factor out x plus 6, leaving behind x plus 2. And this is the factored version of what we started with up there. Okay. That's not nothing, and you can probably see why, yeah, I'm saying this is going to take some work, and you may have come in with factoring skills, right? Some folks listening to me right now may already have factoring skills. If that's the case, then just keep doing that. If that's working for you, if you have some cross method or the box method or some other method, keep doing it that way if it's working. I'm simply providing like a general approach, just assuming that, people don't know how to factor yet. So I'm going to actually skip down just because I ran out of room. Let's try another one. So what was step 1? Step 1 was factor out the GCF. That's already done because, again, x and x, that would be common. So there's nothing common to every single term. Step 2, calculate a times c. A in this case is 1. So a times c is 1 times negative 28. So we do take that negative 28. Okay, factor it. Looking for factors, and I'm just going to actually factor 28. And then we'll look for factors that add up to negative 3. So, factors for 28. Well, sorry, let's do negative 20. I don't know why I said positive. Let's stick with the negative. It's a negative number after all. So, let's see. Okay, so here's what's going on in my mind. I'm looking for factors of negative 28. So maybe I try negative 2 and 14. So if this is the right pair of factors, then this should add up to negative 3, but this does not add up to negative 3. Okay, so you just try again. So negative 28, we want factors that multiply to negative 28 while simultaneously adding up to negative 3. So how's negative 7 and 4? I mean, I'm asking, but I know that works, because if we add these, we do get negative 3. So these numbers are the numbers that I'm going to use to rewrite negative 3x. So over here I'll write x squared minus 7x plus 4x minus 28. So those numbers came in right here and here. And these should always add up to what we originally started with. So negative 7x plus 4x, negative 3x, yep. Factor by grouping was our next step. So I'm going to factor that group and then factor out the GCF of that group. So what is common with respect to x squared and negative 7x? Just an x. What is left behind? An x to make an x squared, and then a negative 7 to make negative 7x. Then factor the second group. So it looks like a 4 is shared, and that's it. So plus 4, don't forget to write the plus, x minus 7, right? No coincidence. These two things are the same. So factor that commonality out, x minus 7, leaving behind x plus 4. It'll always be these pieces out front that is left behind. So the x plus 4 coming from x plus 4. This is our factored version. Yeah, here's maybe a tricky one. I'll go on to this is page 63, part 6. As I was saying, these take a lot of practice, and there's certain tricks that might pop up. Notice that we have this quadratic trinomial, but the quadratic term, which is always the squared term, is written in the middle. So I'm actually going to rearrange this and say n squared plus 6n minus 16. This is our standard form quadratic polynomial now. So step 1 was GCF, but that's already done. There's nothing in common. Step 2 was calculate a times c. That's negative 16. So I am taking the negative. Don't overthink it like I was earlier. It's just the 1 times whatever c is, and c is negative 16. Then factor a times c such that you're looking for things that add up to 6, right? I'm looking at this number here. So let's see. So 8 and negative 2, right? You don't have to jump right to the correct answer. You could just kind of cycle through until you find the right one. But 8 times negative 2 is negative 16. 8 plus negative 2 is 6. So that meets both of those requirements. So these two numbers are going to come in as coefficients on n, re-representing 6n as 8n minus 2n. So we'll have n squared plus 8n minus 2n, and then we still have just minus 16 sitting there. So, right, these have come in as the coefficients re-representing this positive 6n. So now factor by grouping was that next step. So what I'll do is factor this group and this group. So the thing in common here would be n, and we leave behind an n plus 8. Here is a situation where we're factoring this pairing, but we have a leading negative. So just like I said before, my recommendation is to always factor out that leading negative if it's there. So not only am I going to factor out a 2, but a negative 2. So what is left behind after that negative 2 gets factored out? We have an n, and then negative 2 times something should be negative 16, so plus 8. It'll be the same as this if we're doing this right. Then factor out that commonality, n plus 8 times n minus 2. This is the factored version. Okay. So all the ones we've done so far, A has been 1. Okay. A is not always going to be 1. So let's see one where A is 3. So part 1 is still factor out the GCF. I recommend that. So I'm looking amongst all the terms, seeing if there's anything in common. Okay. And I'm not seeing anything. So that part's already done, actually, but it's always good to think about because it will come up shortly. Factor A times C, or calculate A times C rather. So A is 3 and C is 10. So that'll be 30. And then what we do is we factor A times C. This is part 3 now. Looking specifically for factors that add up to 17 if possible. Okay, so you might start with like 6 and 5. That's okay. That accomplishes the multiply part, but it doesn't accomplish the add up to 17 part. So I would just kind of scratch that off and try another pair. 10 and 3. 10 and 3 do multiply up to 30. They do not add to 17. Try again, right? 15 and 2. 15 and 2 work because they do multiply to 30 and also add up to 17. If this is failing, so if you cannot find it, then it might be that this thing doesn't factor. And that would be the math's way of telling us that. We haven't run into that yet. We so far have been able to accomplish this puzzle every time, which means they factor. They have factored so far. So what I'll now do is rewrite this middle term using the 15 and the 2 as coefficients on x. So 3x squared plus 15x plus 2x plus 10. All right, now I'm going to factor this group and this group. You might be wondering, like, what if I wrote it as 2 and 15? What if I did 2 plus 15? That's still 17, that's still 30, but I'm going to have my 2 over here and my 15 over here. It actually doesn't matter. So both of these would work. It doesn't matter, actually. So if I have the 2x here or the 15x here, it doesn't matter. It'll all work out. You'll get the same factorization. So factor by grouping, 3 and a 15. So for sure a 3 will come out of these first two, and also an x. What would we leave behind? An x plus 5. Look at these next two, factor out the commonality. What is common between these two terms? We have a 2 and an x plus 5. If we're doing this right, these are going to be the same. Okay, so then factor out that commonality. We have x plus 5, and it's always these things that are left behind and that go in this next piece. Okay, I'm going to find another one. Let's see here. All right, so let's go on actually to this part here. This is page 64. Part 4. Let's factor it. So part 1, don't forget about it. We haven't actually yielded anything from part 1 yet, but we are about to. So check out the numbers. We have 20, 22, and 12. So all of those coefficients, A, B, and C, are all even. So we can at least factor out a 2, and then I can start thinking about, oh, can I do any better? 4 divides evenly into 20 and 12, but not into 22. So 2 is actually the best I can do. And specifically, I'm actually going to factor out a -2 because of our leading term, right? This is the expression that I'm factoring. Its leading term is negative. So I'm going to actually factor out a -2 and then think about what is left behind. So -2 times what is -20x squared? That would be 10x squared. -2 times what is positive 22x? That would be -11x. -2 times what is positive 12? That would be -6. Okay, so we did factor out the GCF, which is -2. So now what we're going to do is focus on this trinomial. So now we're focusing on this quadratic trinomial inside of the parentheses, and we're going to perform everything that we've been doing on that trinomial. The thing is, we're just going to have a -2 kind of going along for the ride during all that. So part 2, when I do A times C, I'm now using this A and that C. Okay, so this is A and this is C. So 10 times -6, this is -60. And then I'm looking to see if we can figure out factors of -60 that add up to -11. So -15 and 4. I'm just jumping, I'm helping us a bit to save time, right? So these do multiply to -60, and they also add up to -11. So that kind of checks both boxes, right? So I'm going to rewrite this entirety. So I'm going to say -2, and then we still have 10x squared minus 15x now, plus 4x, minus 6. So this is what it'll look like when you had a GCF that actually factored out, right? We actually have this factor just kind of going along for this work. What next? Well, it was the same as what we did prior, right? We factor by grouping. So I'm going to factor out whatever I see as common between these two terms. So we have -2. And then I'm factoring out of that well, it looks like a 5x. So 5x, and what is left behind? I know we have parentheses and parentheses now. That can be confusing. So 5x times what creates this thing? So 5x times, it looks like 2x. And then 5x times what is -15x? That would be -3. Then move to your second grouping, factor out the commonality there. Okay, so plus 2 looks like all we can factor out there, and then I'll end these parentheses eventually. So this parentheses matches with this one. So 2, leaving behind a 2x, surprisingly, -3, right? 2 times -3 is -6. And no coincidence, these two things are the same. So I will factor it out. So -2, still just sitting out there. And then I have a 2x minus 3. And then it's the 5x plus 2 that gets left behind. This is the original thing in factored form. Okay. I didn't have one that didn't work. So I kind of want to, let me make up one here. So what if we had x squared plus x plus 1? We would take a times c, 1 times 1, which is 1, trying to factor to add up to 1, actually. And this just doesn't work, right? Every time, that's a 2. -1, -1, that's a -2. So this polynomial, the x squared plus x, I'm not doing this one. I'm just making up one. Plus 1, we would call that actually prime. Just like when we have a number that doesn't factor, if we have a polynomial that doesn't factor, we call it prime. Okay, on to 6.3. So 6.3 is regarding special products. In my opinion, every product is special, but according to what we're seeing here, there are some special products. This is the first special product. So what this is saying is if you can identify that you have what's called a difference of squares, that you can actually just quickly factor that every time as this. Okay? So what I mean by that is this thing is the same as x all squared minus 9 all squared. So we do indeed have something squared minus something else squared, right? Something squared minus something else squared. So for this problem, A is being played by x, and B is being played by 9. So that tells me that I can just simply write this now. Right? This is equal to this factorization involving A and B. So A goes here, we add A to B. So x plus 9, right? A plus B, x plus 9. And then A minus B, x minus 9. All right. So that is kind of the shortcut approach to factoring this quadratic, what is a binomial. I encourage you often to make connections between things that you've already seen and quote unquote new things. So what I'm going to do is show you an alternative approach that's more similar to what we have been doing. So let's say I did this, again, just a totally different way. So x squared minus 81, I'm actually going to write it as x squared plus 0x minus 81, right? It kind of seemed, I think, like something was missing, that middle x term. If it's not there, then that means essentially a 0 multiplied by it, right? So see how this is actually just a different representation of this same thing. And now we actually have a b to work with. So you can do the a times c approach. A is 1, c is negative 81. So a times c is negative 81. Factor negative 81 and try to add up to 0. So we'd have 9 and negative 9. Okay, then rewrite 0x using 9 and negative 9 as coefficients. So x squared and then plus 9x minus 9x minus 81. Okay, so I'm trying to mimic what we have been doing because you can. And that's what I mean, trying to kind of connect this to things that we've seen already. So factor by grouping, I'm going to factor out of this group an x, leaving behind an x plus 9. Factor out of this group, we have a leading negative, so I'm going to factor out a negative for sure, but also a 9. Leaving behind x plus, right, because we need a negative times a positive as a negative, plus 9. Factor out the commonality. We get x plus 9, right, times x minus 9. Same as what we got before, just kind of a scenic route rather than a shortcut. So yeah, what you're seeing here, these special products are really kind of a shortcut approach. Often the general a times c method works as well. I'll do another one of these. So here, keep in mind, I didn't really talk about it here, but keep in mind the GCF part still applies. So factor out the GCF. Looks like we do have something in common. We have 2x in common, right? And that would leave behind, well, we need to figure out 2x times what is an 18x cubed. That would be a 9x squared. A 2x times what is negative 2x? That would be a negative 1. So that is the GCF, and now this actually falls into this category of a difference of squares, actually, and I'll show you why. This would be the same as 2x times 3x all squared minus 1 all squared. So in this case, we have that a is being played by 3x and b is being played by 1. So I can now just quickly follow this shortcut, and I will still have that 2x up front. So we'll have 2x and then a factorization of this difference of squares. So we'll have 3x plus b, right? A plus b, so 3x plus 1, and then I'll have a minus b. So this is the factored version of that. Okay. There are a couple other special forms. So here they are. So we had a difference of squares a second ago. These are perfect square trinomials now. I encourage you, though, to actually just use the a times c method until you just start seeing this more quickly. So rather than using this stuff, I'm actually just going to encourage you to use the a times c approach. But I'll go ahead and use it once, and then I'll do it another way, actually. So, trying to get this to sync up with one of these, right? This problem is directly under this stuff, so maybe this problem is connected to this stuff. Which one is it connected to? Well, look at the type it is. We have a plus. This one has a minus. This one has a plus. So it looks like this is going to be related to this one. Okay? After that, try to identify A and B. Okay? So we have x squared. So A is being played by x. Then let me write over here, we have 49. So the thing that's being squared there would be 7 squared. So what that tells me is that A in this case is x and B in this case is 7. So in the middle, its claim is that we should have 2 times A times B if this thing is falling into this category indeed. So is it true that 2, right, 2 times A times B, in other words 2 times x times 7, is that 14x? And it is, right? This is 14x. So that means this one is indeed in that category. What that would mean is that it'll simply factor this way. So after I've identified it as indeed falling into this category, based on this middle term working out, right? That is indeed our middle term. Then I can just quickly factor it. So it'll actually factor as a plus b all squared. In other words, x plus 7 all squared. The A times C method works. So I can do it that way if I want. So our A is 1. So A times C is 1 times 49. In other words, it's 49. So factor 49, looking for a pairing that add up to 14. Well, 7 and 7. The reason why this is a special, quote-unquote, quadratic trinomial is because the factors that you'll find are the same. The reason why this one is special, it's for a different reason. It's because the factors that we find are exact opposites. Right? The ones that we were doing previously were not, quote unquote, as special because the factors that we were finding weren't either the same or exact opposites. They were just some numbers. So back to the A times C approach for this one that we've already done. So this is just a verification that we have another way of doing this. We've already done this problem, but I'm just doing this another way. So after you find that, then we rewrite the middle term with these as coefficients. So I'll have x squared plus 7x plus 7x. That's my 14x plus 49. Factor by grouping. We have a group here. We have a group here. So factor out, it looks like an x, leaving behind an x plus 7. Factor out a 7, right? 7 and 49, they share that 7, leaving behind an x plus 7. And notice what's happening here. When we factor out the commonality of x plus 7, what do we leave behind? X plus 7. Something times itself, we usually write as that something squared. So that's our other approach. And we get the same thing, right? Same thing. Okay. All right, I'm actually going to go to 6.4 because I'm starting to get tired. So 6.4 is just kind of a summary of everything I've said so far. So I'm just going to actually do, let's see, I'll just do this middle one. So just go back to basics, right? What was our method? GCF. So factor out a GCF. It looks like a GCF is present, right? We have a 4. And then we would leave behind an n squared minus 4n minus 12, right? If that's difficult still, just hypothetically imagine now redistributing that 4. So that 4 times n squared, yep, that gives us this one. The 4 times negative 4n, yep, gives us negative 16n. And then 4 times negative 12 would be this negative 48. So this is good. Part 2 is take a times c, and I'm using this a and this c, not this a and this c. So a times c is 1 times negative 12, in other words, negative 12. Part 3, factor negative 12, looking for factors that add up to b, which is negative 4 in this case. So we want numbers here such that when I add them, I get negative 4. All right, I can kind of set up this puzzle. So negative 6 and 2, that works. Negative 6 times 2 is negative 12. Negative 6 plus 2 is negative 4. That means this trinomial factors, and we're going to use these numbers as coefficients on b. So we'll have 4. Don't forget that 4 is out front. And then we'll have n squared minus 6n plus 2n minus 12. Okay. Factor by grouping. Kind of said factor weird. And it looks like these first two share an n, right? So I'll have 4. And then inside of that, I have another factorization happening. So we can have factors within factors within factors. It can get fairly complex. N minus 6 would be left behind, right? Again, you just kind of imagine distributing that n back in. We get our n squared from the n times n, and we get our negative 6n by n times negative 6. Move to the second pairing or grouping, factor out the commonality, looks like a 2. After that 2 gets factored out, n minus 6 is left behind. That's no coincidence, right? These should be the same if we're doing this right. Then factor out that commonality. So 4, n minus 6, what is left behind? N plus 2. This is the factorization of what we had here. Whew, all right. Please come to office hours. Please dig into this factoring stuff. It'll pay off. Your hard work now will pay off. But you need to dig in, okay? Talk to you next time. Bye-bye.